Yeah. So hi everyone. I'm Alex Cojocaru. I currently work at the University of Edinburgh, and I mainly work in quantum crypto, but also a bit in post-quantum cryptography and also in query complexity. And we'll actually get to see that all these things are related. Yeah, in this seminar, I'm planning to tell you more about these quantum lifting theorems in the quantum random oracle model. Um, okay, so maybe we can begin. So in this talk, we are going to work in this query model. So in this query model, we are saying that parties are trying to solve a particular problem by just performing queries to a black box random function f. So think of the random oracle as just being like a function f sampled from the space of all possible functions, and then queries in this model look like following: a party sends x and it receives in response f of x. And the complexity of algorithms or adversaries in this model is given solely by the number of queries performed to this black box function f. By the way, can you see my mouse if I'm moving, or do I need to use some laser? Okay. But of course, as we know, quantum computing is bringing a new query model, the quantum random oracle. So in this case, we now allow parties to perform superposition queries of this form. So a party can send a superposition over all x, and it will receive in response from the black box function superposition over x f of x. And as a result, as you know, this is equipping parties and, more importantly, adversaries with more powerful capabilities. So the main goal of this talk and of this line of works is trying to essentially reduce quantum security of a cryptographic scheme to its classical security. So what do we mean by this? Well, ideally, we would like to establish a lifting theorem that you'll hear a lot in this term. But what this actually means is that we would like to ideally say that if we have some cryptographic scheme or some security game that is secure against classical attacks, then we can lift it to also ensure its security against quantum attacks, against quantum adversaries. And a bit more concretely, in these works, we are going to focus on establishing or proving these lifting theorems for security games or security search games in the quantum random oracle model in the first part. So yeah, in the first part, so I'm going to split this into like three different parts. So in this first part, which is a joint work with Huang Garay, Chipeng Liu, and Fang Song, we showed like a lifting theorem in the quantum random oracle model. So specifically, the setting that we are dealing with can be summarized as follows. We have two parties, a classical challenger and a quantum adversary. And the challenger is allowed to make up to k classical queries to the random oracle, and the quantum adversary can make up to q quantum queries. And in this search game, they are also allowed to exchange messages, such that at the end, the adversary outputs a k tuple, so some x1, xk. And then finally, the challenger applies some verification functions, a verification algorithm to this k tuple x1, xk, and outputs accept or reject. And we say the adversary has won if it resulted in the challenger accepting. So this notion of lifting theorem was originally introduced by Yamakao and Zandri in 2021.
Alex, sorry, can I interrupt to ask a silly question?
Please interrupt me. Yeah.
So in the previous slide, you said it's a search game. So what part is search? Like it's accept, reject, it seems, right? So I thought maybe it sounds more like a decision game, but
yeah. So it's called search mainly because of what adversary needs to output. So as opposed to in the sense that the adversary in the end needs to output like a key tuple is very important. So maybe if you think a bit in a non-interactive setting, in which let's just suppose that the adversary needs to output a single thing, then we cannot make it a decision problem. So it needs to be like a search problem in which the adversary really needs to output something long. And we'll see that it's like a very crucial point, because otherwise it would have some super big implications that we don't currently know how to tackle yet.
Like Ambani's thing.
Exactly. So we are not are not claiming anything about. I mean, that would be like something very interesting, but we currently don't know how to
And what problem should I keep in mind? Like, what would be like some canonical problem to keep in mind here?
Yeah, so we're going to use this example a lot, but think for now of like function inversion. And because we are in this multi-query setting, think of like multi-image inversion, which is kind of like the task in which you are given k images and you need to output k different pre-images. So I think in general, a lot of like either image inversion or collision finding, these are very natural examples.
So the challenger just checks if it's the correct pre-image somehow.
Exactly. So then it's also important to think of like how many queries does the challenger need to make. Obviously, if it's an image inversion, then k is equal to 1. If we ask for a long, like a more intricate problem, then k can grow very large.
I see. Okay, thank you.
We are interested in both cases, in both the case when k is constant and when k grows very large. I think that's going to be an important distinction.
A quick question. So here k is the security parameter?
Not really. So it's more like a specification of the problem.
Okay.
Because I guess it depends on how you think about it. So like going back to Atul's example, if you think of like the multi-image inversion problem, you can say that there the task is given k different images to output k pre-images, one for each of these images. So this is still not necessary. This is still not like a security parameter, because the security parameter would be given by how you actually choose the domain and the range of the random oracle.
Right.
But it's more part of like the actual problem specification.
Okay. Yeah. Thank you.
Yeah. So so this notion was already like introduced in 2021 by Yamakawa and Zandri as a tool that enables lifting security from the random oracle to quantum random oracle. And at the high level, you can think of the result as saying the following: that if you have a search game like the one you have seen here, and in this game the challenger only needs to perform a constant number of queries, so this k is constant. And if one manages to prove that this game is secure against a classical adversary, then automatically this game also becomes secure against a quantum adversary in the quantum random oracle. So this is what kind of like you should think of it as what lifting means. But a bit more concretely, let's try to make this statement a bit more concretely. So what they actually show is that if in such a game the challenger makes k classical queries, and some arbitrary quantum adversary can win this game using Q quantum queries with probability epsilon, then one can also construct another classical adversary for the same underlying game that only needs to perform k classical queries that can win the game with probability at least epsilon, so the probability of the arbitrary adversary A, divided by roughly 2q to the power of 2k. We can pause for a second here, but then we can also get a bit more concrete. But yeah.
So how does it apply to Yamakawa Zandri? Like doesn't it seem to like what am I missing?
Yeah. That's a very good question. So is it maybe fine if I go to a simple example first, and then we can discuss this, because I think maybe we can get a bit more information there, because we can also see how this is interpreted. And but yeah, that's a very good point. I actually also wanted to bring this up, but just to maybe get things more a bit concrete, because for now still like these quantities maybe don't say much, and I want to show like the function inversion example to show you why this bound is actually not that bad.
And here, this is a special case because one, we are assuming that k is a constant, and two, we are assuming that the challenger only makes k queries.
Exactly. So actually, the thing that the challenger makes k queries, you don't think of it as an assumption, because in any game we know how many queries the challenger needs to make, because challenger is honest and it is fixed by the definition of the game. But yeah, it is an assumption to assume that k is constant.
Yeah. Okay. Thank you.
And this is actually something that we will try to improve when we exactly grow k larger to see what happens. Yeah, that's a very good question. Okay, so with this beautiful ChatGPT generated images, this is how I think of like quantum lifting. That's from a lot of quantum queries, you go to a very small number of quantum queries. But kind of like to me, the main takeaway message is the thing that these lifting theorems are useful because they essentially tell us that if you want to cite a security against an arbitrary adversary that performs Q quantum queries, well, then it actually just suffices to study the security against a bounded adversary. So what do I mean by bounded adversary? An adversary that only needs to perform a small fixed number of queries. And then if you establish some hardness for this, you can then plug it into the quantum lifting theorem, and that gives you like an upper bound on the success probability of any arbitrary adversary. Of course, the question is how good of a bound this is. And we will see later that we are still a bit far from getting always the best bound. Okay, so our main result essentially, so for the first part, our main result essentially establishes like an improved quantum lifting theorem. By improved, what we mean is that we get a better bound. So more precisely, we now say that let k be the number of queries of the classical challenger. Then for any quantum adversary A making Q quantum queries, we can construct another quantum adversary that makes exactly K quantum queries. So the same number of queries as the challenger. That can win this game with probability, at least the probability of the arbitrary adversary A, divided by this quantity in red. So divided by 2 to the power of 2k, multiplied by q plus k, choose k squared. And similarly, the takeaway message is that now, if you look at this inequality over here, one way to interpret it is that if you want to cite the upper bound on the success of any A, well, then it actually just suffices to study the security against a bounded B, so against a quantum adversary that makes exactly K quantum queries. And this inequality would already give you like a hardness result against any A. That's sort of like the main takeaway message for all these lifting theorems. So yeah, if you have any questions here, I'll pause it because yeah, you will hear a lot of these repetitions. So I think it's important to kind of like understand what it says. And we will discuss this bound in a minute. So for now, it's just about how we plan to use it and not the exact bound. Okay. So if there are no other questions, we can move on. So one way of thinking about it is that it's kind of like a generalization or like an improvement of this lifting from a random oracle to quantum random oracle. And this is also like a question that you were asking at the beginning. The simplest setting you can think of, and this is why we call it search game, is that the adversary receives some challenge. Then the adversary responds with some k-tuple. And if this k-tuple specifies some relation R defined by the game, then we say that A wins. And the most basic example is the function inversion. So in the function inversion, we are saying that an adversary is trying to find the preimage of 0 for some random oracle H, and then challenger only needs to perform one single query to verify adversary's answer. So this clearly satisfies this. Or if you really want to match it with the search game definition, you can think that the challenge from C would be just the image 0, and you need to find one. So maybe here I can show you a bit like the difference between the two different bounds. So our bound is this one in red, and then the Yamakaw's entry is the one in brown. So it actually, at a high level, our improved lifting theorem gives like a better bound or an improvement in loss by a factor of k factorial squared. So of course, while this makes no difference when k is constant, it actually turns out to be quite useful for showing some other applications like non-uniform security, some multi-instance security hardness, and some direct product theorems that I'm going to explain in a minute. But again, to kind of like understand this a bit, this improvement, let's also look again at the function inversion problem. So actually, it turns out that if you want to use Yamakawa's Henry lifting, you can already show that since k is equal to 1, so challenger only needs to perform one query. And then by plugging the fact that the hardness of solving the problem with a single query is going to be 1 over n. So because a classical adversary with a single query cannot do much better than 1 over n, then this already tells us that for any quantum adversary equipped with Q quantum queries, the maximum success probability is roughly of the order of Q squared divided by n, which we know it's actually tight because of Grover. So already Yamakawa's Henry gives like a tight bound for constant k, or at least for k is equal to 1, but also for small k. But then, as you said, if we now think of like the generalization of this problem, in which you need to find k different inputs that are all mapped to the value 0 for an arbitrary value k, then it turns out that the Yamakawa's Henry bound is actually is actually a bit far from being optimal, because they can recover essentially this bound over here, kt squared divided by n, while we know that the bound optimal is t squared divided by n to the power of k. So in fact, they are a factor of k to the power of 2k away from being optimal for the hardness of this problem. But then if you actually use our lifting with this being our loss, then we can actually show that because of the fact that any algorithm equipped with k queries can win this game with probability at least 1 over n to the power of k by simply just making random guesses, then we can actually show that our bound is tight. So for k function inversion, we can get a tight bound, which is recovered by Grover. So the main takeaway message is that this k to the power of 2k factor is actually quite significant when we go in the arbitrary k regime. So it allows us to recover tight bounds. Okay. But also something like that I find quite interesting is that these lifting theorems, as we have seen, they allow us to prove some quantum security, but also some query complexity results. But importantly, by just classical reasoning. So what do I mean by classical reasoning? Well, we can use this fact, or we can show this fact that for any algorithm that makes exactly k quantum queries, the success probability of such an algorithm can be upper bounded by some purely combinatorial quantity P of R, where R specifies the winning relation of the game that we want to study. So this might look a bit complicated, but in most cases, it's actually quite straightforward to compute. So this P of R specifies the probability that there exists some permutation pi, such that if you sample a key tuple uniformly at random, and then you permute it according to this permutation pi, the result is going to belong in the winning relation of the game that you want to study. And kind of like very nicely, this PFR quantity, as you can tell, it only depends on the game. So of course, it has no dependency on the adversary. And as I said, because it's just like a classical combinatorial quantity, you only need classical reasoning to compute it.
Alex, sorry,
Yeah.
I have a very dumb question. So when you write so I'm trying to parse how you understand the condition. So you're saying that if y1 to yk is uniformly sampled, then you want that, after applying the permutation, it belongs to the relation.
Yes.
So you want this event to happen with some probability in the condition? Like, I'm not fully sure.
With probability 1. Like I want to compute the probability that there is some permutation such that this condition always holds.
So is it? Can I rephrase it as follows? Can I say that for all y1 to yk, it is true that its permutations satisfy the relation? Is it equivalent to saying that? I'm not sure.
Sorry,
because you're saying it's with probability 1, right? Then isn't it just the same as saying that for all y's it should hold that the permutations belong to the relation, or am I missing something?
Oh, sorry. Maybe I didn't say it in the right way. But essentially, the probability is that there exists some permutation, right? So we are not giving away that there exists such a permutation, because otherwise this PFR would always be one, right? If there would always exist some permutation, yeah. So maybe I messed up when I read it out loud in order to quantify it.
No, you did not. I'm still not. Okay, so there exists a permutation pi such that if y is sampled uniformly at random, I permute it with pi, it will belong to R for all. Okay, I'll think about it later. I think I'm getting a bit confused. It's fine. Carry on. I'll check later.
I mean, this is not actually like a very crucial part, but it's more like saying, I think it's like the main advantage of this is just saying that actually it turns out that if you want to establish all this quantum harness, you just need to compute this quantity. So you don't even need to do any quantum. You can just do like classical combinatorics to establish quantum harness. And then you can establish this by combining the two things. You can establish like an upper bound by this PFR. I will go into the details, but now just to give you like a list of this. So using these lifting theorems, we can kind of like in a straightforward manner show a series of applications. Some of them are quite simple and natural, like the multi-instance function inversion or collision resistance that you have seen, but also some notions of security like non-uniform security and salted security. And also we can use it to show some version of direct product theorems in the average case, in the quantum random oracle. While from what we know previously, only worst case direct product theorems were known. Okay, so maybe to just give away a definition of what this direct product theorem is. It's kind of like a general tool, but very powerful, that allows one to say what is the harness of solving G-independent instances of a problem, or in our case, G-independent instances of some search game. Each of these games given a separate independent random oracle, given the total number of cumulated resources. So in our case, given G times Q quantum queries. I won't go into a lot of details, but essentially we can show a direct product theorem that establishes what is the harness of some quantum algorithm equipped to the total number of cumulated resources to solve all G independent instances of a game. And maybe just to emphasize a bit, this is not always very straightforward, because you may say, okay, but why not I just solve all the, let's say, search problems separately, and then obviously I can just accumulate the probability. But it's not always clear. Maybe you can sometimes do something smarter and combine two instances at once. So this result is not so straightforward. And
is there like a canonical problem, like some simple problem where the direct product theorem does not hold? Just to keep in mind, like
where solving the independent instances is not optimal. Oh, that's a very good
question. Is there like some simple counter example that people give often, or?
Yeah, I'm not sure. I don't think I can. Let me see. Yeah, I'm not entirely sure. I don't want to say something that might not be true here.
Yeah, I'll look it up later. Don't worry. I just thought I'd ask quickly. Yeah, no worries. Carry on.
I'm pretty sure there must be, like, even based on search, there must be something, but I just don't know if. I think probably like just standard search would not be a good example, but maybe some more complicated search version would give away already that.
And another small thing I wanted to ask was that in crypto, like assuming that you have independent random oracles or independent oracles, is that okay? Like you solved them somehow, and that's how you assume that you have independent oracles. Is that the idea, or?
So it's more part of like a setup assumption, right? In which you are just saying, for instance, that you have like two different random oracles. You are given away that they are like independent, and then maybe one needs to solve, like, let's say, a recursive problem in which you first find a preimage for the first random oracle, and then you plug it into
Got it.
second problem that requires the second oracle. So it's more like a, if you want, like a setup assumption or something like that. So you don't need to prove it or anything like that.
Okay.
I guess probably. Yeah, I was going to say that maybe even like the Yamakawa example you gave falls into that, but no, I'm not even sure if you really need to assume that those are independent oracles. Probably you can even assume that it's the same oracle for all queries. So yeah. Yeah, to be honest, actually, I don't think I've given it enough thought of what all this means in the context of Yamakawa's entry. So we can also discuss this at some point, but because you mentioned at the very beginning, but I don't know if it would have like any interesting implications.
We can discuss that later. It's I think they solved it to get around these kinds of issues, but it's okay.
Yeah, but I don't think it would definitely not say anything new, because we cannot establish just new like hardness results, and it would maybe recover some things from there. Okay. Yeah, so again, maybe this is just to show that in a quite straightforward way, so we didn't have to do any additional work, but because of because of the improved factor and because of like known results in this non-uniform setting, we can also essentially give an upper bound on the success probability of non-uniform quantum algorithms that are equipped with both quantum queries and as bits of classical advice. So we can also get this kind of like quantum preprocessing upper bounds. And now I can go back to some more basic examples. Those are more like kind of like generic things we get, like the direct product theorem and the preprocessing. So again, as mentioned, we can use it for the multi-image inversion problem. So to make it a bit more concrete, in this case, an algorithm or the adversary is given as challenge a k-tuple, y1, yk, and the task is to invert all images in this vector. Another very simple example. Sorry, I forgot to mention that as we have already seen, for multi-image inversion problem, we can actually show that the bound is tight. On the other hand, if we go to the multi-collision finding problem, which, as you may guess, is just the task of finding k different inputs x1, xk, sorry, that are all mapped to the same image. Unfortunately, for this one, we could not show any tight result. So it's also a bit tricky, because you may say, okay, but maybe it still leaves like some room for improvement in your current bound. But then the fact that we already get like a tight bound for multi-image inversion, this suggests that the generic tool cannot be a lot improved. But maybe if you kind of like specify some conditions of a problem, so if you put more assumptions on your problem, then maybe you can try to get something stronger. But it's very unclear how to do that, because there is not much you can say about this problem, about this multi-collision problem. And similarly, there's like another problem useful in proofs of work, in which you need to find k different inputs all map to 0. And finally, some simple but cute problem in complexity theory, which is the free sum in the random oracle, that you need to find 3 different inputs that are mapped by the random oracle to 3 images that sum up to 0. So all of them are very simple problems that we can directly apply our lifting theorems, because they fall into this definition of security search schemes. So now I don't want to go into like a lot of details, but I just want to mention a tiny bit about like what one needs to show, or like what are the tools needed for proving these kind of results. So maybe you have heard of
Alex. Sorry. Can I interrupt before you start? I think you already mentioned this, but I didn't fully grasp what you were trying to say. So you mentioned that this also applies to the case of non-uniform adversaries together with salting to prevent non-uniform attacks. Could you say a bit more about how you handle that case, or will you do it potentially later?
Yeah, so I don't think there's like I don't think I'll have a lot to say in here, because basically this kind of like just follows there are like some papers that actually study this trade-off between time and space, and particularly I fail to remember all the others, but I think two of them are Kai-Ming Chung and Chi-Peng Liu, that they already showed this result that if we have like a specific bound between like a specific bound like the one we recover that gets that for the success probability of any quantum algorithm with some additional loss in terms of the number of bits of classical advice, you can also get an upper bound on the success probability of non-uniform adversaries.
Okay.
So it's almost like a direct plug and play type of theorem. I can say that we can recover it because we get a very specific tight bound that previous works are not able to rely on.
Okay. Thanks.
Yeah. So kind of like one of the tools we need to use is just this measure-and-reprogram technique. So in terms of quantum random oracle, we know there are like a few frameworks and tools that we need to use, that people use in general to establish bounds. We don't need to like rely on the recording technique that I'm sure some of you are very familiar with. We instead just need to rely on this measure-and-reprogram framework. And we need to introduce a new version of this reprogramming that essentially allows us to get all these better bounds. So at a high level, you can roughly think about it as an improvement of the adaptive reprogramming of the quantum random oracle on multiple points by two works of Don et al. That from now on I'm going to refer as the FMS. And in particular, our framework yields some tighter reprogramming bounds. So at a very high level, the main observation in this very nice work of measure-and-reprogram of the FMS is that consider a quantum algorithm that performs Q quantum queries, and now carefully measure K out of its Q quantum queries. Then the point is that these measurement outcomes, these K measurement outcomes, will correspond to the final output of the algorithm. Of course, it won't always do that. It will happen with some multiplicative loss of order q to the power of k. But the kind of like main interpretation is that if you just measure some of the queries of a quantum algorithm, then with certain probability, this would correspond to the final measurement outcome of the algorithm. And of course, the loss can be quite significant because you are just doing like a measurement of these queries.
Okay, Alex, I'm missing something extremely trivial here, because like suppose there's a quantum algorithm, right, that just makes Q queries, okay,
Yes.
and then just outputs like something independently uniformly random.
Yeah, but then that initial algorithm would also have like a very low probability of solving your problem. So I'm just saying that this loss is not about the loss of solving the problem. You should think of it as the loss compared to the original algorithm that performs the Q quantum queries. So I think what you are describing, if I understand correctly your question, is some naive algorithm that uses those Q queries in a very
stupid
bad
way.
way, in a very bad way, and then output something completely random. That algorithm would already have like a very low probability of success. What the FMS says that take even this very bad algorithm, I'm measuring K out of the queries. Of course, I'm not going to get anything meaningful, but what is this saying is that this new algorithm is going to succeed with at least the probability of the bad algorithm multiplied by some quantity.
Okay, so then my follow-up question would be that suppose you're trying to output some say some subset of the strings that you query, like maybe you're outputting say the first n by 2 bits of the queries that you're making, Suppose say that is the it's just a syntactic problem, right? Like when you're saying that you make k measurement and you just use that as the final output, these k measurements would be, for example, n bit measurements, right? N qubit, whatever, like whatever the domain of the random oracle is. But what if the output is not to output the the output is not an n bit string, right? Suppose that the output was like an n by 2 bit string. So how does it syntactically make sense what you're saying?
Okay,
Is my question making sense? I am not even sure. Maybe I'm missing something obvious.
Maybe let's try to parse it. I'll try to parse it to make sure I understood correctly. So now you are talking about like the length of the output of the algorithm compared to the length of the quantum queries made by the algorithm. Is that correct?
Yes, because the algorithm is, you're saying it's outputting, it's measuring k of the quantum queries and it's using that as the output, right? So that's why I'm getting a bit confused, because I thought the output could be like some function of the queries that are being made rather than just the queries themselves. So I don't know how to syntax.
Good point. Yeah, that's a very good point. So here in this context, I'm making the simplifying assumption that the output also comes into like as in the examples I showed, comes into like some inputs to the random oracle. So for instance, you have like some quantum algorithm
like
that can
pre-images or something like this.
Yeah. I think this can also be generalized, but here just to simplify,
I see. Okay.
I'm just making this assumption. Yeah, that's a very good point. Sorry.
Okay. Thanks.
Yeah, that's a very good point. Okay. So basically here our observation is actually is just saying that now instead of just measuring these queries of the quantum algorithm in a one by one fashion, in a sequential fashion, why don't you just add them into a separate register? In other words, we are just saying, okay, measure these queries in a coherent fashion. So what do we mean by this? Well, we mean that each query is going to be added into a separate register, and then with something that we call the controlled reprogram oracle query, we can progressively at the same time reprogram the oracle and run this algorithm with the updated oracle. And what is kind of like bias? So maybe this is where you also see why this k factorial comes into play, because now we are only going to measure these reprogrammed inputs as an unordered set at the very end. So recall, DFMS measures them in a particular order, like one by one, how they chose it, while we keep it in a separate quantum register as an unordered set, and then we are just going to measure them at the very end. So this is kind of like where this k factorial squared comes into, because of this difference between ordered versus unordered. And this kind of like,
Alex, are you like copying the query into another register and then measuring them later? Is that what you're saying? Or
exactly. Yeah.
And you're saying copying is somehow not the same as measuring still.
Yeah.
Okay.
I mean, I have like some pseudocode. I'm not sure if it would help, but yeah, I think I can also maybe pause for a second here. I mean, the idea is not very complicated. Of course, it's just like a lot of words that is not very precise. But the main observation is that, yeah, maybe let me try to restate it again. So EFMS says, okay, I want to be able to guess this guy's output. I'm going to measure them in a particular order. Well, what we say is that the actual order of the queries is not important. If I already know that the output is going to be extracted from here, why should we care about order? So how can we do it instead? Well, we'll just keep all these quantum queries, or we'll add these quantum queries to some other quantum register that is going to be preserved coherently. And then when the algorithm is done, only then we are going to destroy this and check what's in that register.
So intuitively, Alex, the way we normally think about measurements is that if you make a copy into another register, it looks like that already essentially serves as making a measurement. Right. So somehow that is not what is happening here, even though you're saying you're copying the state, the register. So can you comment a bit on why that is? Like why it is different from just measuring it? it's not so clear to me, right? Because
maybe
like, for example, if I have
also to the code and
I see. Yeah, like I was just thinking, like, so for example, if you have a superposition of x0, say you queried at x0 and then you queried at x1, and there's like some superposition. If I make a copy of this in a different register, right, then the reduced state becomes mixed, right, on the query register. But yeah, somehow saying it still stays coherent. So I'm a little bit lost. Maybe I have to.
So it's kind of like we need to modify a bit the query operation. That's why I call it like a controlled reprogram Oracle query, because we won't just copy. We will. So in this sectional register in which we want to keep all this information, we will add them in a way that still maintains like a set structure. So in a way that doesn't break all these requirements. So you do need to check something that, for instance, if this query hasn't been made before, only then add it in this set.
I see.
So in this way we don't violate what you just said.
And is it using the compressed Oracle to do the simulation?
This is not using any compressed Oracle at all. Yeah, that's yeah. I mean, in fact, yeah, the reprogramming on multiple points is sufficient for all this. I don't think necessarily, or at least I don't see what whether recording technique could help at all.
I see. Okay. Good to know. Okay, thank you. Please carry on. Sorry for the interruption.
No. Please. I mean, these are all very good questions. Yeah, but sorry, maybe for those of you that are not very familiar with what it means to like even reprogram a random oracle, it's kind of like saying that I start with like a random oracle H, and then the reprogrammed oracle H to output Y on input X is exactly the same function, except that on input X, we impose it to output Y. So it's kind of like hard coding a specific input-output pair. And obviously, one can also generalize it to like vectors of X and Y's. So if X is now X1, Xk, and Y is Y1, Yk, then we can do this reprogramming in a sequential fashion. So this is also like the reprogramming theorem. So if you haven't seen this before, I think this is quite a powerful tool. And I will just say our version, but you can pretty much see this reprogramming in a lot of previous works, as I mentioned, like the FMS, but also a way longer list of similar works. So what this says is that like a reprogramming theorem, you have like two random oracles H and G. And then you have like some arbitrary quantum algorithm A that makes Q quantum queries. And then you consider some arbitrary input vector XO and the output vector YO. And then the idea of the reprogramming is that it says that there exists some simulator that gives an oracle access to the two random oracles and to A is essentially able to simulate the output of A having oracle access to the reprogrammed oracle. So to the reprogrammed oracle on input vector XO, output vector YO. And the success probability of this simulator is going to be at least the probability of the arbitrary adversary A having oracle access to the reprogrammed oracle divided by some quantity over here. While when I say correct, we define with respect to some predicate that our problem establishes. And this is kind of like, as I said, this is like the main tool to prove all these lifting theorems and all these harness results. And of course, what is important here, I'm not sure if I already mentioned it, is the number of queries that the simulator needs to perform. So this simulator also only needs to make k queries. So this is kind of like the most important tool that we need to rely on. And maybe just to try to hopefully answer a tiny bit Atul's question, if this would bring some light in how this works.
Sorry, Alex, can you go back to the previous slide for just a second? I got a little bit lost. Sorry, just give me a second. It says that there exists. Right, so the simulator is able to produce an upper bound on the correct solution with some loss.
The objective of the simulator is to kind of like simulate the output of the algorithm A, but which now has access to the reprogrammed oracle as opposed to the original oracle. And then we want to put our bound on the success probability of this simulator.
Yeah, so sorry, and then what do you want to do? You want to lower bound the success probability of the simulator.
Yeah, we want to say that the simulator succeeds with at least this probability, with a decent probability. It's kind of like what we originally said. So
is this probability? Okay.
So think of the very basic DFMS result I mentioned. The DFMS says that if you are able to just perform key queries, then you are able to simulate the output of the algorithm. So we are trying to do something here, also with like a small number of queries. But of course we want to say that the simulator succeeds with at least this probability. We want to construct, because this simulator we need to show how to construct it. So we need to show a quite decent algorithm that is able to simulate the output of A.
Right. Yeah, because normally, like my intuition was that somehow we would think about an algorithm that has access to the unprogrammed oracle, and we would want to say that after programming, it doesn't change too much.
Yeah, that's kind of like a different setting. So I think you are more thinking of like maybe this kind of like hybrids in which you say that you have some adversary and it cannot distinguish whether it has the original
I think I'm thinking
something you programmed.
But here we were supposed to. So how does it relate to the algorithm which has access to the normal oracle? As compared to the because at some point you have to go back, right? Like you have to.
But actually, sorry, I was about to say that your intuition is quite close, because we are going to use it in this way. So we are going to say that we have the algorithm A. We then are going to replace it with some. We are going to replace the oracle with a reprogrammed version of that, and then we can construct a simulator that is saying, oh, if you have access to the reprogrammed oracle, then I can come up with like a very good solution for you. So your hybrid is in there, which is going to be used in the security analytics. It's just that that part is not the most difficult one. The most difficult one is showing that you can do this reprogramming in this way. You can simulate the output.
Right. Yes. So that jump is a separate argument, which is
exactly.
handled separately.
So that is mostly just used inside like the proofs, but that is not very, very difficult to show. But yeah, that's a very good point.
And you want to show like an upper bound on the probability that A would succeed, essentially, right? That is the point.
Yeah. So okay. Think of it. Yeah, maybe let me just quickly go back to recall you what's the kind of flavor we want to show. Remember that we always wanted to give this kind.
Like with direct product, for example, you cannot do much better than doing it individually. These kinds of things.
Exactly.
Got it.
So you can also maybe think of this B that you always see here as the simulator. The simulator is trying to interact with this challenger, able to simulate the output of A.
Right. And the reprogramming part would just say that it doesn't change much, and then you say that the reprogrammed one has some upper bound. Okay, got it.
Yeah, exactly.
Yeah, so sorry, I got confused. Thank you.
No, it's actually all very good questions, and because I'm skipping like a lot of details, and so please, but also please let me know if I should go over some other things faster.
And in the prior works, this denominator was some larger quantity.
Yeah, it is larger quantity only with respect to K. So as I mentioned, if it is constant, then there is no loss. When K is larger, then roughly we get this kind of like improvement, like a K factorial squared, which for problems in which you really need to output like a very large K tuple or like a such problem in which you need to output like K different solutions, this can make a difference. But kind of like, okay, I'm also trying to build, so it's not just about the improvement, but as hopefully I'll have time to cover also a bit later on, we can also generalize this kind of like lifting theorems to like other settings, building on top of this. So it's not all about, oh, I'm getting a slightly better bound and I'm very happy. We can actually show that it's not very difficult to generalize it to other classes of adversaries, or even different types of model without actually too much extra work. So, but I mentioned this bound because I guess this was like one of the original motivation. Yeah, but at least I want to. So yeah, I can mention a bit this. I don't. How much more time do I have at all? So
You're going too fast on this
no,
slide.
no, no. That's why I want to see how much because I guess
You
I
have like you have about I think 30, 40, about 40 more minutes.
okay, good. Yeah, I just thought that I also need to stop a bit before that. But yeah, so if you want, I can explain a bit about this measure-and-reprogram experiment, or otherwise, if you are comfortable with the things, you can also just
Oh
go
no,
to the
explain.
okay.
I only understand a subset of what you explain anyway. So
Yeah.
at least
Okay.
explain.
Good. Yeah. So the measure-and-reprogram thing starts as what we originally said. We want to decide on some queries to be reprogrammed. It's not super important here, but if you're wondering why is this q plus k, it's because for simplicity we also assume that the adversary makes some additional k queries on its solution. So the final solution, that which is this k tuple, which is actually in relation to what Atul was asking earlier, like what about like the size? We are assuming that the final solution is going to be again queried by the adversary at the very end, so that those queries are stored. Okay, so this is actually kind of like also interesting. In addition, we also need to choose uniform at random sum vector B that kind of like decides whether we should do the reprogramming before or after the query, so before or after the adversary queries. And this is where this adding queries in a separate register happens. So this is where like the modification maybe from like the normal query setting occurs, is that we are now going to run the original algorithm A with some additional control register R. So essentially we can consider like some unitary that updates this control register, namely for any X that hasn't been queried yet. So in other words, that hasn't been stored yet. If it's going to be queried, then if it's going to be queried and it hasn't been in L already, we are now going to add it in the recorded set L. So this is the part I was mentioning, namely instead of just measuring A's queries, we add them into this separate register, into this separate set L. And now we kind of like, let's see how we actually run the algorithm in the online stage, like in the live manner. So let's say A A makes its ith query, then we check whether I is equal to Vj. In other words, we check whether at the very beginning we decided to reprogram this ith query or not. If it was already selected to be reprogrammed, then now we need to make a decision based on the value of Vj, namely whether we first make the query and then update the control register, or the other way around. And kind of like crucially here, this controlled reprogram oracle operation, this is what allows us to both reprogram the oracle in a progressive fashion, but and also at the same time run the algorithm with this updated oracle at the same time. And of course, if this query shouldn't be reprogrammed, then we are simply just going to answer its query normally. So we don't need to store it or anything. And then at the very end, the algorithm is going to output some vector x, some input vector x and some output vector y, which is the thing that Atul was asking about the assumption of the algorithm. And what we do instead, now we are going to finally measure all the information we have gathered in the control register R. So in the control register R, we have stored this superposition over all these sets L. So now we are going to obtain some measurement outcome L in the form of some x prime, y prime. And finally, we just check whether we were lucky and this x prime was equal to x. if this x prime was equal to x, then we simply output xy. It means that our guess was correct, and otherwise we abort. And that success probability that you have seen comes into saying what is the probability that this x prime is equal to x. And because of the way we are storing this information, it turns out that it's only this factor away. So this is basically just a description of all this controlled Oracle query means in a tiny bit more formal way.
Right. Sorry. Let me just go through it a little bit more carefully. So B is basically specifying, whether you're going to reprogram it or not.
Oh,
Alex is like, shut up and let me move on.
No, sorry. Actually, I don't know what I pressed, but it started going on its own. Sorry.
Okay. Right. So B is basically saying, right. So okay. So like you say here in the fourth point, you're saying if B is 0, okay.
I think you are touching an interesting point, which I don't have like a very good explanation. Namely, why do we even need this B? Why do we even need to care whether you are doing like first the reprogramming and then the query, or the other way around? And I think it's actually just for like analysis purposes, like in the sense that we need to introduce this variable, but and all these previous reprogrammings do it as well. But in none of them, it's actually very clear why this is intuitively needed. It turns out that it just needed for like the actual proof, which annoyingly it always introduced like a loss of 2 to the power of k. But apart, and when I say for the analysis, is that okay? I don't think I have a slide with this here, or maybe I do. So how do we actually show this? You can actually show that if you look at the decomposition of the states of the algorithm and the composition of the state of the simulator, you can go from one to the other. So it's like a very, very nice decomposition that essentially considers what happens when a query is equal to Vj, depending on the value of Vj, and you can show like a decomposition into a lot of like subnormalized states that are going to match one state in the composition of the simulator with one state in the composition of the adversary. So this is like all very, very nice and beautiful. And this is where this Bj is used, but it's just for like this mathematical decomposition. Intuitively, we don't know why this is really, really needed. It's just like an artifact required for the.
Okay. I have to admit,
I think I eliminated the slide with the composition because it looked way too messy. But maybe I should have kept it to explain a bit how this goes. But yeah.
Yeah, I think I'm a little bit. Yeah, I'm not able to fully follow the intuition, but okay.
So if I learned about Vj, don't worry about it. Like I don't think it has. It's just like a math artifact.
I see. Okay, so I don't think about B for the moment. So then I'm just thinking that okay, so you have this unitary, and then you're recording the query into this coherent register R. So far I'm with you, and then when A makes its ith query, that's the B business. Okay, so that's fine.
Yeah. But think of like this step 4 as the one in which we actually run the algorithm, right? Or the one in which we kind of like try to simulate the algorithm by looking at his behavior and then trying to like replicate it in our own fashion, in our own way.
Okay.
So this is like the live part when we actually need to run it. Yeah. So it should be like a for loop.
Wait. No, but then when you're running the algorithm, right? Like suppose it makes the first query, and then when it's making the second query, it already expected the answer to the first query, right? So I would have imagined like it can make adaptive queries, right? Like depending on the answer to the first one, it could make the second query.
Yeah.
So already in step 3, you are giving it access to the Oracle, right? Or not?
No, so step 3, okay, step 3 is not really like I shouldn't make it like a step. Step 3 is just describing how we are going to run the algorithm A. Okay, maybe I got a bit confused. I would just like step 3 is more like a bullet point explaining what are the operations we are going to do
I see. Okay.
For the queries of A.
Okay. Got it. I see. And then you measure R to obtain. Okay, and then the R register, because you measure the database register in a sense, right? To get L equals X prime Y prime. But I would have thought that the register L is, oh yeah, it's a vector. Okay, so you have a bunch of X's and a bunch of Y's, and you output XY if X prime vector matches X vector. What is X vector? What is the X vector here?
Yeah,
it's the output.
I think of it as being like the output. So you can either think of it as just being like the inputs, and then the Y vector are like those final K queries I mentioned to you, in which you just are also querying the X to the random oracle and you get Y vector.
I see. Okay. Thanks.
Yeah.
Okay. Good. Got it. Thank you.
Okay. No. These are all very good questions, and sorry, I just didn't know whether I should make it more technical and explain it like all the decomposition, but I didn't want to make it look too ugly. But yeah, these are all like very good questions. Okay, so now I was going to like jump to like the second part about like some extension, but yeah, maybe there are like more questions about any of this theorem or about this measure-and-reprogram. I can take like a small pause here. Okay, but also if you have like any questions, please let me know, and I'm happy to go back. Okay, so in the second part, I just wanted to mention like some extension of our work for like a bigger class of adversaries. So the setting is pretty much the same, but now we are interested in also studying the security against noisy intermediate scale quantum adversaries. Maybe like the first result, which is kind of like central for all these lines of work, is an extension of the lifting theorem, but adapted to hybrid adversaries. So these are those adversaries that are equipped with both classical and quantum queries. And essentially, the hybrid lifting theorem says that if we have in the same search game that you have seen before, if the challenger performs K classical queries, then for any adversary equipped with Q quantum and C classical queries, we can construct another hybrid adversary that makes K queries in total. That can win the game with probability, at least the probability of the arbitrary adversary A, divided by roughly Q squared divided by K squared plus C over K having the power of K. And similarly, the main takeaway message is that this is again going to be particularly useful because it essentially tells us that if you want to study the security against any arbitrary hybrid A, well, it actually just suffices to study the security against a bounded B, so against a hybrid B that performs K queries in total. And similarly, as you already know, the main reason why we are interested in this hybrid and not just treat hybrid as a quantum algorithm, because obviously any classical query can be treated as a quantum, is to get better bounds. Because just imagine that if you look at this expression over here, if we would have treated this C as also part of the Q, then we would have got like a worse bound because we would have just got Q plus C squared everything under K squared, which is a worse bound. So in other words, we want to treat classical queries separately. We don't want to treat them just like a special case of quantum. And maybe from like a more practical point of view, this is also a bit motivated because in general, we expect algorithms to have more classical queries or more classical resources than quantum resources. So that's why it falls into this NISQ picture. But yeah, in particular, we kind of like look at three classes of adversaries, and it turns out that they're very related when it comes to the quantum query model. So you have seen the hybrid algorithms that are those equipped with classical and quantum. Then we look at noisy oracles. So these are those algorithms that can perform quantum query to some oracle OP. So P is like a fixed probability parameter. So this oracle behaves as follows. So you send him like a quantum query, and with some probability P, the input and the output registers of this quantum query are going to be measured. Therefore, this query is just fully classical, and for probability 1 minus P, this is just like a standard quantum query. And finally, because they turn out to be very related, we also look at quantum algorithms that have a bounded quantum depth. So I'm not going to read this expression out loud, but essentially for all these three classes of adversaries, we can establish like lifting theorem. So we can establish like a lifting theorem for like upper bound for the success probability of hybrid algorithms. Similarly, an upper bound for algorithms that perform, let's say, T quantum queries to a noisy oracle. And similarly for algorithms that have quantum depth at most D as a function of some bounded algorithm that only performs K quantum queries. So here I won't go into like all the tools, but I do want to mention one thing that similarly as you have seen the measure and reprogram, what we need to do this time is to come up with like a version of this measure and reprogram, but adapt it for hybrid algorithms. Because again, we want to have like a very good loss that also takes into account like classical queries. So we need to introduce this new measure and reprogram framework, and from this we can establish all these lifting results. And I want to just show like the difference in terms of how this reprogramming theorem works as opposed to the previous quantum reprogramming. The only main difference is that now we allow for like an arbitrary hybrid algorithm that has great access to the oracle H, and then we can construct a simulator, which is again going to be a hybrid algorithm, but that performs the same task. So the simulator still, its objective is to simulate the output of A that has oracle access to the reprogrammed random oracle. And of course, the loss is going to take into account the number of classical queries as well. And very importantly, we show that the simulator, which is kind of like the quantum adversary B that we have seen in the previous lifting theorems, is going to make exactly K queries in total. So quantum plus classical sum up to K. Okay, so basically for this, I won't go into like the details, but I also wanted, because I guess it's about like 20 minutes or so. If that's fine, I can also mention like about the random permutation model. But if there are more questions here, I'm also happy to.
Yeah, so what is intuitively the key difference in the way you do the reprogramming? Because for like, how do you handle the classical queries differently from the quantum queries?
Yeah. So in terms of like how the actual reprogramming works, this is like how the simulator actually looks like. This is not going to be very different, but it's more about how do you handle a classical query in the decomposition. So think of it in this way, and this is true even for like compressed oracle, in case you are familiar with that. So there you are not actually going to change how a classical query is going to be done to a compressed oracle. The classical query is going to be dealt in exactly the same way from like a simulation perspective. The only difference is how much a classical query can contribute to your final objective. So because in like in the compressed oracle, but also something here, you have some notion of kind of like a progress measure, or how much it contributes to you getting close to a state. And of course, what you want to capture is that a classical query should have a much smaller step compared to a quantum query. So in our case, we need to be a bit more careful when we consider like this decomposition of the algorithm that performs classical query and quantum query, that we need to treat separate like the classical query. So we need to consider a bit of a smarter decomposition for that doesn't add too much
I see.
Coefficient, like to be coefficient for those terms. But the simulator looks exactly the same, so that's why I haven't added it here.
Okay. Okay. Thank you.
Yeah. And yeah, maybe for the remaining part, I want to mention something about like permutations, because I think it's like I mean, it might look like a very similar object, but it turns out to be way more complicated in general. So yeah, maybe just to have like a quick recap. So in the classical query random oracle model, we just assume that we have like some random function f, and then parties can perform queries of the form x and receive in response f of x. Then in the quantum random oracle, parties can perform superposition queries to similarly classical random function f. But in the quantum random permutation oracle model, we now assume that f is a permutation. And what is also different is that now all these algorithms or adversaries can perform superposition queries to both f and the inverse of f. So so the adversaries have way more power here. Okay. So similarly, our goal is to try to achieve lifting theorems, but now we want to achieve lifting theorems in this quantum random permutation oracle model. So the type of search games have like a very similar setting in the sense that still we have a challenger that can perform k classical queries, and some quantum adversary can perform up to q quantum queries. And in the end, the adversary outputs some k tuple that needs to pass some verification function. But of course, what is different is that now both the challenger and the adversary can perform queries to both the permutation and to the inverse of the permutation. And just to mention kind of like two models, I'm going to mostly talk about the first one, but also I'll mention the second one in case you'll see this for like other applications. So the main model is the query permutation model that we have discussed, in which parties have access to pi and pi minus 1 for a uniformly random permutation, so sample from the space of all permutations. And there is like a second model called the ideal cipher model. So in this one, you sort of like assume that you have some parameterized permutation, parameterized by some k, and now each party has access to both ek and to the ek minus 1, where each of these ek is going to be an independent random permutation.
Wait, sorry. So I didn't fully understand the ideal cipher model. So you're saying each party, you said that there's a permutation indexed by k, and each party has access to ek and ek inverse. So is it the case that the kth party has access to e sub k, or all parties have access to the family?
So yeah, even in this model, we still have like only two parties. We only have like a challenger and adversary. So don't think of k as being a party. K is just like an index for your function. So it's more like maybe it's kind of like a distinction between talking about like a function and a family of functions.
Okay.
That's
how should I think about k? Is it like a constant with the security parameter? Does it scale with the security parameter, or like?
I think generally it should have a security parameter. It is something generated by some. You have like some. Again, think of like maybe the case of like family of functions, and then you have like some generating algorithm that outputs you like an index for the function that you are going to work with, and that index of the function scales with the security parameter.
I see. So is it like a salt? Should I think of it? Maybe is that a reasonable way to think about it? Like that?
Oh, yeah. I guess that's also one way to think about it. I'm not sure if it's like a very formal relation.
Okay, got it.
But yeah, I think that's also one way to really think about it. And maybe just to give you like some motivation. So a lot of these constructions and proofs that are also currently in use are in this model. So you probably have heard of the Even-Mansur cipher, like the Davis-Mayer hash function, or this more famous sponge construction, also known as Shafri. But now I think I just want to mention a bit about like very conceptually what is the main distinction between random oracle and random permutation. Because still they look pretty similar objects. The main distinction is that these random functions, as you have seen, they have like perfect independence. What do I mean is that if I take two inputs and then I look at the corresponding outputs of these two inputs, the outputs are going to be pairwise independent, right? But now, if you look at the random permutation, obviously because it has some structure, namely we know that the function needs to be injective and it's moreover an permutation, they're kind of like being almost independent. So they have like some weak correlations because of all this structure that the function needs to preserve, being a permutation. And it's kind of like all these weak correlations that in general invalidate all the methods we know in the quantum random oracle. So maybe as a short history, as you already know, we had this compressed oracle framework that Atul described for like quite a long time. But in general, we didn't have like any really good frameworks for analyzing random permutation. So I think there has been like some very nice series of work that in the end culminated with like finally a compressed oracle for permutation maybe like a few months ago. But it took like a long time until people were able to come with this. And I should also mention that all these difficulties occur even when the algorithm or like the adversary has access only to the permutation, like only to the forward one, let alone the setting in which we give them access to both. But because as we have seen in the definition, the algorithm has access to both pi and pi minus 1. And of course, when you can create the inverse of the permutation, then you destroy all this independence. And similarly, you can just think that this pairwise independence no longer holds. So
sorry, Alex.
Yeah.
I think I'm missing something very basic. I thought if you had a permutation, a random permutation, and a random function, but only forward, right? Like only pi and say only whatever f, then essentially those are indistinguishable with whatever polymany queries. Is that not correct? I forget what.
I'm actually not sure. I'm not sure of this result. That would be something interesting. I'm not very familiar. I mean, at least in our case, the complications seem to be even when we have like forward access, but I'm not aware of this result.
Because like that would mean you can invert it, no? Because like you have to find a collision. It should be equivalent to finding a collision for a random oracle, and that should be essentially exponentially. Maybe Venkata knows actually.
Yes, I think so. If you just had oracle access, then these two are similar. But if you want to do something more like record queries, then things become difficult.
You're saying the techniques sort of start failing,
Yes.
but they may continue to be. But if they're indistinguishable, couldn't you just say that, look, they are indistinguishable and then use the techniques from random oracle?
But okay, so that is only for proofs which only require, which are in this non-programmable random oracle or a non-programmable random permutation model, where the adversary only rather in the proof, we don't need to program the random oracle.
Why would that make a difference? Okay, maybe you can explain it later then. Okay, that is an interesting point. Okay, thank you. Yeah, we can. I'll ask you.
There's these different. We can talk about it later, maybe.
Yeah. But thank you. Yeah, I didn't know that. Thanks.
Yeah, so maybe I'll just briefly mention a bit the main result, and then I'll mention some of the main challenges. And just to give you like some flavor of like the other difficulties in this case. So again, like the lifting theorems has like a bit of a same flavor. It's saying that for any quantum adversary that makes Q quantum queries, we can construct a classical adversary that makes exactly K queries, so the same number of queries as the challenger. That can win the game with probability, at least the probability of the arbitrary adversary A divided by this quantity here. So the size of X is the size of the domain of the permutation. Okay, and yeah, the same takeaway message that it suffices to just focus on the hardness of this bounded algorithm B. So maybe I'll just quickly mention some of the applications to kind of like see why we even care about this, and then as I said, I'll mention some of the challenges. So we can derive some new quantum query complexity bounds. So the main example that you should keep in mind as we talk about like function inversion here, in this case we have something called like the double-sided zero search game, and I will explain in a second this is because I think it's a very natural, nice example. But also we can show like some post-quantum security. So in particularly we can use it to show post-quantum security like pre-image resistance, one-wayness, or multi-collision resistance for constant round sponge, and also collision resistance of Davis-Meyer. So this double-sided zero search game, you can now think that you have like random permutation defined on 2 n-bit strings, and you are given oracle access to both pi and pi minus 1. And the task is to find this time a pair, xy, such that pi of x is equal to y, and moreover, x and y must have at least n leading zeros. So this is kind of like the main focus, the main problem we want to focus. It's again a non-interactive search game. You are given oracle access to this, and you need to output such pair. Okay. So it's actually not very hard to once you have like this lifting theorem to analyze its hardness, because it's quite clear that k is equal to 1. The challenger only needs to make like one query to verify the solution of the adversary, and then so therefore it just remains to study what is the max success probability of a guy that performs one query. Well, then the probability of that guy is going to be at most 2 to the power of 2n. Because it can just come from like two situations. Either algorithm just queries a valid pair, or it just makes like a random guess. And then we can actually show that the probability of a general quantum algorithm is going to be at most q squared divided by 2 to the n. And by combining with this result, we can actually show that our bound is tight. And also, in general, it doesn't have to be stick to like this task of finding this pair. We can generalize it for any arbitrary relation R. So we can show that the probability of a quantum algorithm winning a game in this random permutation model is going to be at most q squared divided by the q squared multiplied by the probability that you can win using a single query to find a pair xy in some arbitrary relation R. And similarly, we know this is a tight result due to Grover search. Okay. So this is kind of like the main example you should keep in mind. Now I'll just mention again like a tiny bit history if you are interested in this SHA-3. If not, I can go a bit faster. But for this sponge construction, so this is this hashing algorithm underlying SHA-3. And it's kind of like interesting that classically we know for like a very long time that this is as secure as random oracle, but in the quantum case, we didn't know that much, at least until maybe 1 or 2 years ago. So we knew that this sponge had satisfied like pre-image resistance and one-wayness for like single round. But in general, no results were known for like multi-round sponge. So using the quantum lifting, we can show all these properties for constant round sponge. While concurrently there was like this very nice work that showed indifferentiability for multi-round sponge, but using more specific tools adapted for sponge. And then I believe the even more recent work of Caroline showed probably something similar, but using a very nice general framework. And also we can use it for like Davis-Meyer, that are these hashing algorithms that are behind SHA-1, SHA-2, and MD5. So similarly, in the classical world, we knew for like a long time that they satisfy one-wayness and collision resistance, but quantumly collision resistance was open, and we can show both the properties using our lifting. Okay,
so just to go back, so for SHA-2 and SHA-1 and MD5, was it known that they're as secure as a random oracle in the whatever random permutation model at least, or?
Yeah, you mean the classical world?
Yeah, in the classical world, basically the analog of the sponge construction.
Yeah. Exactly.
But for
Exactly.
okay.
Yeah.
And what about the other way, like the SHA-3? Is it? Do we know anything in the ICM model for in terms of security for SHA-3? Or
so I don't know actually how. I don't think these constructions can just go from like one model to the other, because it would kind of, I mean, it's like a different construction, right? So for instance, maybe if I understand correctly your question, I don't know if you can just
I see.
automatically
I
transfer
understand. Yeah.
one directive into one to the other.
But random permutations are stronger than, like, it's a stronger model than ICM, is it, or is it just a different model?
I think it's different. I don't know if
Okay.
at least I'm not very like it's not like any instrument. To me, they're a bit incomparable. But
I see. Okay. I thought one of them is more general, because like you had a family in one case, while in the other you had only one. So I would imagine that the family is more general, but you're saying that's not necessarily the case. I'll ask you later. Carry on. You have only 5 minutes. Conclude the talk first. Sorry. I'll ask after.
Yeah. Okay. Maybe I just actually wanted in the last minutes. I actually just want to give you like some idea on like why it's a bit hard and what one needs to do. Okay. So let me see if I have 5 minutes. Okay, maybe I'll just mention this a bit quickly. So let's go back to the original lifting theorem in the random oracle, and think of the function inversion task in that problem. So the main kind of like takeaway message is that if you consider like the lifting theorem in the simple random oracle, and you consider like some algorithm. This is, by the way, classical observation. So what I'm saying now is just like classical. If some classical algorithm outputs some x star as the proposal for the pre-image, there are only two options. Either x star was queried by A or x star was never queried. And we can denote by I star the index of when that query happened, or like perp if this query never happened. So the main observation in this original lifting theorem is that this algorithm cannot distinguish between the following two situations. In the first case, it had oracle access to the reprogrammed oracle from the very beginning. And in the second case, the algorithm has oracle access to the original H up to the point of querying the solution. And after querying the solution, it has oracle access to the reprogrammed oracle. I think this should be quite intuitive, because obviously if you haven't queried that point, how would you know which oracle you have access to? So based on this observation, you can define like this very simple simulator that can simulate A with access to the reprogrammed H. So I won't go into the details, but this is basically the main observation that allows one to construct a very simple simulator that can simulate the output of A, having access to the reprogrammed H on input X. But unfortunately, this very nice observation is going to fail even in the classical random permutation model. And for now, we switch back to our double-sided search problem. So what do we want to show about this simulator? Let's take exactly the same simulator. The simulator is going to try to behave the same way as the reprogrammed oracle given to A. But now we have all these weak dependencies in the permutation that you have seen. So let me give a more concrete example. So what was the simulator trying to originally do? So the simulator here was trying to guess what was the index of the query in which A performed the query to the solution, right? So I star was the index of the query in which X has been queried, right? So now the simulator, let's say, is trying to do the same thing. So it's going to try to make a guess about this query. But in the permutation, but it is still possible that some previous query let's call it I, return exactly the same value as the value we want to reprogram, like pi star of x. But then it just means that now we have created a function. So this function over here, this object over here, this pi reprogrammed on x, that now there are two inputs that are mapped to the same value. So there is some x prime that under pi evaluates exactly to the value of pi star of x. But then this object is not even going to be a permutation anymore. So this is like a very big concern.
But why is that a problem if it's not a permutation? Because like you're reprogramming things, right? So it's not necessary that you can detect whether it's a permutation or not. So
yeah, but that's exactly like the next bullet point. In principle, it doesn't have to be like an issue. You don't need to ensure that it's always, but it is an issue if the algorithm is able to detect such a thing. And kind of like this is what the example was capturing, because now our algorithm A was performing two different queries. The x prime that, let's say, we assumed it performed, and the x that are now contradicting the whole injective structure. Of course, my example doesn't say that it's always happening. I'm just making the assumption that if such an x prime exists, then this whole falls down. This is obviously not an attack in general, but we just don't know how to handle such situations because this is clearly a big issue. And of course, this is only even in the forward case, as I mentioned, this is just breaking the injective structure, even when the algorithm has access to the forward permutation, let alone when you have access to the inverse as well.
Yep.
Sorry, I can go back to this point if it's not very clear, but I think this is one of the main crucial parts. But maybe in the remaining minus 1 minute or so, I just want to mention like what kind of like one needs to try to do. So it needs to do like the reprogramming of some special queries in a very careful way to kind of like avoid all these inconsistencies. So what you need to exactly take care of like this situation I just explained before. You need to look at the queries that we are going to call hits with respect to the outcome. So in other words, you are going to look at the queries that are going to be reprogrammed. And you also need to look at the queries that lead to this collision situation. So you need to look at those queries X that we call miss, that the original permutation pi led to the reprogrammed value. And then you are going to do this reprogramming in a careful way, such that you maintain injectivity. And I had like a nice graph picture, but that would take a bit long to explain. But roughly speaking, you are going to do the reprogramming permutation, taking these branches into account. So if your input is a hit, then you simply output the reprogrammed value, pi star of x star. Then if it's going to be a miss, in order to maintain injectivity, you output the original permutation pi applied on x star, and otherwise you don't do any reprogramming at all. So just to kind of like repeat, if you just hard code this as you would normally do in the random oracle case, then you violate the injectivity. So our solution is instead to maintain injectivity and to make it indistinguishable from the adversary's point of view, then you need to reprogram the hit and the miss queries. And similar things will need to be done for backward queries as well. Okay, maybe I'll just try to wrap it up here. So now what the simulator needs to do, you not only need to guess whether this I star has been queried by A, but also what is the type of this I star query, whether it's a hit or a miss. Because in this way, we can we can model what is the first query that touches the outcome X star. So by touches the outcome X star, it doesn't mean that it's just X star. It can also be like one of the neighbors of X star. So think of it as in a graph. You also need to look at the vertices that point to this X star. Those also need to be reprogrammed. And we need to come up with like a quantum measure and reprogram lemma in the permutation case. But okay, maybe I can jump a bit over all these things, and I can just go directly to the conclusions. Okay, so maybe I'll just end up with this. Yeah. So maybe I can just mention like some future directions that are very natural, and I'm sure you have already thought about it. In general, maybe can we try to get like some tighter lifting theorems? As I mentioned, we only know how to get it for this multi-image inversion problem. So I think this would be like something quite neat if you find maybe some settings or some assumptions that you put on the game to get like some tighter bounds. We also don't know how to extend it to general interactive games. So this is something that I think you were asking me at the beginning. For now, we are just considering like this kind of like a non-interactive setting, but we don't know how to make it for like a full general game. And yeah, of course, other things could include like, can we find like other applications, or maybe if one knows like any other NISQ interesting settings to extend it. Yeah, thanks.